Hey, welcome back. Glad you're still with me. So we are still talking about electrons. And now we've looked and we've realized that electrons are not in circular planetary orbits about a nucleus. They're actually we don't really know where they are. That's what the uncertainty principle told us. We don't really know where they are, but we can kind of get these probability diagrams that tell us approximately where they are based on their energy, and it tells us their shape and their orientation. If we take, again, those quantum numbers, which are based on Schrödinger's equations, the quantum numbers give us an idea to talk about where these electrons are and what the electron configuration of an element might be. So when we look at this, remember one thing that we did state, I don't think we gave it a name, perhaps in the last video, but we need to talk about the Pauli exclusion principle, which says no two electrons can have the same values of all their four quantum numbers. So I don't think we stated it like that, but what we said is that every electron in an atom can be defined by that set of four quantum numbers. And again, just a quick review, remember n is our principal quantum number that tells us the energy. So we have our principal quantum number. We have L, which is our angular quantum number, but again, really, that tells us our shape. We have our ML, which is our magnetic quantum number, which tells us the orientation of that shape, magnetic, or MS, which tells us, again, the spin. It's the spin quantum number, tells us the spin of electrons. And so, remember what we were talking about is that each of these suborbitals could have two electrons that occupy each of them as long as they had opposite spins. And that's really what the Pauli exclusion principle is telling us, that every electron we have to be able to identify by its quantum numbers. And then once we do that, we can start looking at the electron configuration of that element or of that individual atom. And so sometimes this is referenced in pop culture about no two objects can occupy the same space at the same time, and I don't know why cat jokes are so nice, but something about them. Anyway. Okay, remember, ultimately, the reason why we're interested in the quantum numbers and the quantum number sets for these electrons is we're interested in the electron configuration of the elements, because again, that tells us how they're going to react chemically. So again, remember, we looked at a periodic table that was laid out like this, and it was laid out in terms of our quantum number sets. And so the reason, again, there's two rows right here is because these are what we call our S block. These are S-shaped orbitals. And again, remember, they're all the same shape. The only difference between a 1s and a 2s is 2s is just going to be a bigger sphere. 3s is going to be further out, but they're all sphere-shaped. And again, there's only one orientation of a sphere. So again, if we go through our quantum numbers just quickly, so n equals 1 we'll take, but again, this could be n equals 2 or 3 or 4 or 5 or 6 or 7, because each energy level starts with an S shape. L then is 0. That is the definition of our L shape. So if we're at n equals 2, well, we still start at L equals 0. Again, our S shape. Remember, there's only one orientation of that S shape. That is our orientation. It can be plus or minus L, so it's only 0. So that makes sense. There's only one orientation of a sphere. And then again, our MS is plus or minus 1/2. So we can fit 2 electrons into each of those. Again, once we get over into larger orbitals like our p orbital, well, then it completely expands. Right now we have 3 different orientations or 3 different suborbitals, and each one can fit 2 electrons for a total of 6. And again, they don't start until we have a larger quantum number, until we're at the second energy level. Then we can have that L equals 0, which we do right here. But again, now we've added another shape, which is L equals 1. Because again, remember, L can be anything up to n minus 1. Okay, we don't need to review much more of that. Now we just want to look at, writing out either those quantum number sets, or better yet, what we're going to call orbital filling diagrams that shows where those electrons go, basically in this setup, so what they look like. So again, if we start with hydrogen, where n equals 1, and L equals 0, and ML equals 0, and then MS can either be plus or minus 1/2. Well, again, we have 2 quantum number sets, right? Plus 1/2 and 1, 0, 0, minus 1/2. So there's 2 possible electrons that can fit into that 1s orbital. Notice hydrogen just has one of them. So it doesn't have 2 electrons. It only has, well, maybe this one, maybe a plus 1/2 spin or a minus 1/2 spin. Helium obviously would have both. So what we could do is we could write orbital filling diagrams to show what these things look like. A lot of times what our orbital filling diagrams will look like is what they'll do is they'll put energy here. So notice this really, and going back, this is really just the periodic table. So the sections of the periodic table, but it's written in an orbital filling diagram sort of manner where we're relating each of our orbitals to the energy that they have. So again, this is our first S orbital. Going up from there is the 2s to 2p. After 2p, we go to 3s. And this is kind of a tool we can use to help us put together our orbital filling diagrams. And we will as we go forward. But right now, we're going to skip by it first so we can learn some people's names. I don't know why we need to know people's names, and we really don't need to know people's names. But there are questions that ask about them. And we actually do need to know their rules before we start trying to put electrons in places. So the first rule is the Aufbau Principle. Okay, not a rule, it's a principle. It says that when we do orbital filling, we always build up. Aufbau actually is not a person's name. It's actually a German word that means to build, or building up. And so that's what we're going to do, is we're going to build up the electron configuration using orbitals of increasing energy. So what Aufbau Principle means is if we know how many electrons an element has, say we're talking about, sodium, and sodium has an atomic number of 11, so it has 11 protons, and it has 11 electrons, and we said, well, where are those 11 electrons? Well, we can't just say, well, maybe one's here, and we'll put one here and here. So they can't just go all over. We can't put these 11 electrons wherever we want. The Aufbau Principle tells us we need to fill those lowest energy levels first, and then build up from there. So every element has to have its own unique set of quantum numbers. That's the Pauli exclusion principle. Aufbau is telling us when we do write our orbital filling, we have to fill the lowest energy levels first. One other rule, and I don't know why this is Lord of the Rings themed, but our last rule is Hunds Rule. So the other one is principle, this one is a rule. And this is named after a person, the other one's a German word. I don't really get too excited about the names of things as long as we know what the rules and principles are. And this one says that electrons, they do not pair up in a suborbital, okay, unless they absolutely have to. And that's when we get into p orbitals. So if we're at a 1s, so let's do hydrogen based on this rule. So if we have hydrogen has one proton, it has one electron, and if we go back to our energy filling diagram, well, hydrogen can only put an electron here in the 1s orbital. So if we were to write an orbital filling diagram, sometimes they make boxes. I don't like to make boxes because then I get too messy. I just make a line. I label it 1s and say, well, it has one electron. And it doesn't matter if my spin is an up spin or a down spin, it has one electron. So this is an orbital filling diagram for hydrogen. If I did helium, now helium has an atomic number of 2, so it has 2 electrons. So we have to fill this 1s orbital first, and it can have 2 electrons in it. Again, as long as they have opposite spins, and so we do want to show them having opposite spins. We do that by showing an up spin and a down spin. Again, this is based on our spin quantum number, so these two electrons would both be in the first energy level. So principal quantum number 1, they're in an S shape. Our angular quantum number is 0. There's only one orientation of that, and then they have opposite spins. Now, once we get beyond there, now we're beyond the 1s level. If we go back to our energy filling diagram, now notice any element beyond helium is going to have a full 1s level. And so then we go into the next energy level, which is our 2s. And we can see that on this energy level diagram, or we can find that on the periodic table. Notice if we read the periodic table like a book, from top to bottom and left to right, notice in the first row is 1s. We can fit 1, 2 electrons. After we're done here, well, we go back and start here. Now we're in the second energy level. We fill our 2s. After we've done that, then we go straight across and into our 2p. So we can always read what orbital we're in from the periodic table as well. After 2p is filled, you'd go across, go down into the third energy level, then we're at 3s, follow it across, and so on. So I'm going to use this periodic table as a guide, and you know what? I'm going to do that element I said before. I said sodium has an atomic number of 11, so it has 11 protons, but then it also has 11 electrons. Well, I want to write this orbital filling diagram for sodium. Well, just like the Aufbau principle says, we have to start at the lowest energy level, which is a 1s. Well, again, a 1s has one orientation, can fit 2 electrons. 1, 2. So that takes away 2. Now we have 9 electrons left to fill. So if 1s is filled, then we go down to the next line and we're at a 2s. Well, a 2s still has one orientation, and we can fit 2 electrons, which we have plenty. We have 11, well, 9 left, but we can fill our 2s electron. Now notice after 2s, then we go into our 2p's. And here's where we have to remember that in our 2p's, we have 3 suborbitals. We have 2px, 2py, and 2pz. And that is determined upon where that p orbital, remember it is kind of a dumbbell shape, and the x, y, and z are telling us which axis that dumbbell shape is aligned along. And if you think of a dumbbell, you can think of, well, we can turn that 3 different ways, so that kind of makes sense that there's 3 orientations. So I have my suborbitals for my 2 p's written out, and there's 3 of them. And again, remember, each one can fit 2 electrons. Here's where Hunds' principle comes into play, is that each suborbital is going to have 1 electron in it first. So all the suborbitals, which are at the same energies, are going to get 1 electron first before we go back and pair. And that is because these are electrons. And if we put them in the same orbital, well, electrons are all negative. So they're going to repel each other. So they're going to spread out into the available. I like to think of it as the kind of the bus seat rule, that when you get on the bus, you're not going to sit next to somebody else. I mean, maybe if they're for your friend, but say you get onto a public bus and you don't know anybody on it. Well, typically you're not going to jump into the seat where there's already another electron. You're going to go into any available open seat before you go back and sit next to somebody else. And sometimes you'd even stand up. But anyway, so how many electrons have we filled? 1, 2, 3, 4, 5, 6, 7. We had 11, so we still have some to fill. So that's 7, 8, 9, 10. Now we're full. Well, if we filled 1s, and we filled 2s, and we filled 2p, well, then we need to go to our 3s. So here's our 3s orbital. We have 1 more electron, and boom, it is right there. So this is the orbital filling notation for sodium. It has 1 electron in its 3s level. Notice if I looked at sodium on the periodic table, and this is one that kind of has both things on it, I kind of could have predicted that. Notice where sodium is. Sodium is right here. It's in the 3rd energy level, and it's 1 step into the s block. So it makes sense that its outside electrons are a 3s orbital. So in 3s, it has 1 electron. And again, that is really what's important about all of this, is how many electrons are in that outside orbital. So let's grab the periodic table here. What the different periodic tables you can see, doesn't matter, has the same information we need. And let's do a different element. Let's say, let's do sulfur. So sulfur, atomic number 16. So sulfur has an atomic number of 16. That means that also a neutral sulfur is going to have 16 electrons as well. Again, by the Aufbau principle, we need to start at the lowest energy level first, which again is our 1s level. And I'll bring our little periodic table here back so we can use it as kind of a guide. So 1s has 2. Again, after 1s is filled, we go down and we're in 2s. So 3, 4. After 2s is filled, again, 2s can fit 2 electrons. We're into the 2p. 2p has 3 orbitals, a 2px, a 2py, and a 2pz. And you don't have to write x, y, and z, but I like to just to keep track. Again, we're going to put 1 electron in each suborbital before we go back and pair based on Hunds' rule. So now we have 2, 4, 6, 8, 10 electrons. We're not done yet, so we're going to go through that one. Now we're down to 3s. So in 3s, again, we have enough electrons, so that is full. 1, 2. And now after 3s, we go across and we're in the 3p orbital. Again, it's a p orbital, so we can have px, py, and 3pz. So we have 3 orientations, so 3 orbitals in every p orbital. And now we have 4 electrons left. So again, 1, 2, 3, and then we go back and pair. And it doesn't really matter which one we pair, but typically we pair the first one. And it also doesn't really matter if these are x, y, and z in the right order. Those orders don't matter. It just matters that we have 3 suborbitals, and that we only pair after each one has been filled. Every sublevel in that energy level. Okay, so here we have our orbital filling diagram for sulfur. you can notice that as we get bigger, this is going to get more and more complex as we get into D's and F's. And that's where you might be happy to know that we actually have a different way to write out orbital filling notations. Typically, we don't write out orbital filling notations that get much bigger than this because they get big and they get sloppy. I mean, think of what happens. Notice we get into 4s next. And notice after we fill 4s, we fill into 3d. And that might be a little bit kind of crazy for you to think about. Because now what's happened, if we look at our energy level diagram, is we were plotting along just fine. 1s to 2s to 2p to 3s and 3p. And you'd like to go into 3d, just like it shows here. But the problem is that 4s is actually slightly lower in energy in 3d. So 4s actually gets filled first. And then we go to 3D. And that's not hard to remember, again, as long as we look at the periodic table. If we look at the periodic table, we'll see that, notice 3s goes to 3p, and then, reading left to right, we go into a 4s. And we know it's 4s because we know it's 1, 2, 3, 4. We can just count on the columns as long as we remember that d orbitals start in the third energy level. So we actually fill 3d before we go back and fill 4p. It's kind of stuck in the middle. So maybe what I'll do here, just so we have one example, is we'll look at scandium. So scandium is a transition metal, so it's in our 3d orbital. And scandium has, well, it has an atomic number of 21, so it has 21 electrons. So right now I've filled up for scandium through 3pz. So all of our 3p's are filled. So we have 1s, 2s, 2p, 3s, 3p filled. We have used up 18 electrons, so we have 3 left. So we have to go back down here to 4s. Well, 4s, even though it's a big number, it still is an s orbital. So it still can hold 2. And now we have 1 more electron. That 1 extra electron goes into the d orbital. Here's what you may not like, though, is even though we're not going to use all the d's, if we're writing orbital filling notation, we have to write out each suborbital in the d. So we're in 3d, and 3d has 5 different orientations. And if we take a quick look back at their shapes, here's what they are. Again, remember d orbitals don't start till we have L equals 2. The only way we can have L equals 2 is if we're at n equals 3. So we're in the third energy level. We have L equals 2. That's a d orbital. And again, our ML values then can be -2, -1, 0, 1, or 2. That gives us our 5 orientations. And this is what those shapes look like. Sometimes they're called cloverleaf. And notice our basic ones are aligned between the axes. So this is dyz because it's between the yz axis. Maybe you can't read that. I'll make it bigger. Here we go. We have dxy. That's between the x and y planes. We have dzx, which is between the z and x axes. But then we have some crazy stuff. X squared minus y squared, which is aligned along the x and y axes, and then dz squared, which is everybody's favorite d orbital, which has a donut, and then loads of probability. Again, these are all probability graphs, remember. Anyway, there are 5. That's what's important. And it's important to recognize their shapes, maybe to be able to draw 1 or 2. Don't worry about drawing all of your d shapes exactly. I'm going to label them just because I like to. So xy, xz, yz, x squared minus y squared, and dz squared, which again is everybody's favorite. Anyway, we have 1 more electron. Where does it go? Well, it has to go in one of these orbitals. It doesn't really matter which, but we do have to show that there are 5 available. So it has 1 electron in its d orbital. So we could go on and we could do this, and we could write orbital filling diagrams. Notice they do it here with boxes. For any element we wanted, we just have to start again at the 1s, go to 2s, 2p, 3s, and obviously we could go beyond there like we just did. However, we're not going to do that very often. We're going to switch over to something called an electron configuration. You do have to be able to do both, but just realize that electron configurations are a little bit more useful for us. So what our electron configuration is really just a shorthand for our orbital filling diagram. If we look at it, now we are just writing down the energy levels. So the first number is the energy level, the 1, the principal quantum number 1. That's our energy level. We write the shape down, and then the superscript is how many electrons are in that spot. And so if we look at these, it's pretty easy to convert them. So 1s has 2 electrons, so 1s2. 2s has 1, so 2s1. Notice 1s2, 2s2 is our electron configuration for beryllium. 1s2, 2s2, 2p1 is our electron configuration for boron. We have carbon, we have nitrogen. Important thing about nitrogen, by the way, is nitrogen, because once you have one electron in every available suborbital, there's actually a level of stability with that. So just as a side note, if you have a half full subshell, this is called paramagnetic. And there's some level of stability with that. Now, once we get down here to neon, and then we have a noble gas, notice what we have when we have noble gases is we have full, all of our orbitals that are there are full. And again, remember what we know about noble gases, that they are stable. And this is why they're stable, is because it has nowhere to bond, nowhere to share electrons. What we're really seeing when we're looking at these orbital filling diagrams is we're seeing, hey, notice this? This has spaces. This has spaces either to gain electrons or to lose electrons, so it can participate in bonding. This has an electron here, so it has an ability to bond, gain or lose an electron. When we see an orbital filling diagram like neon and we see it completely full, what we can predict is it's probably not going to react. So down in the corner we'll see an orbital filling diagram for fluorine, and what I'm going to do is convert this into an electron configuration. It would be 1s2, 2s2, 2p, and then we look at how many there are, 5. And notice when we look at that orbital filling notation, we'll notice that there's one spot missing there in fluorine. That is one reason why fluorine is so terribly reactive. It is one short of having what we would call an octet, or noble gas electron configuration. Our noble gas electron configuration has a full S and P orbitals, and our S and P together, our outside S and P, are always called what we call our valence electrons. And our valence electrons are the ones that are going to be involved in our bonding. So they are very, very important to always look at our S and P. Those are the ones we really want. And in fact, there's another way, shorthand, to write electron configurations. Because you can imagine, just like orbital filling diagrams, when we get into really big elements, we're going to have really crazy electron configurations. So here, let's look at our element zinc. And let's write this, its electron configuration. So its orbital filling has been done. So if I converted this to electron configuration, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, because it's full. Wow, look at it, I already ran out of room. Okay, sorry, this was where I ran out of room. So, like I said, we had our 1s2, 2s2, 2p6, 3s2, 3p6. Here's one thing that's kind of confusing as well. A lot of little things that are confusing. Typically, when we write the electron configuration, even though the D fills after the S, we write them in numerical order. So we'll write 3d10 right here, and then we'd write our 4s2 last. And don't ask me why, and not all places you see that, but often, especially in the US, that is the format that they typically use. So we don't put them in the order they fill in, we put them in numerical order when we write the electron configuration, just to make it one more thing that's more complicated. Okay, one thing that's important to know, though, is again, we're really only concerned with the outside electrons. And when I mean the outside electrons, I mean the row of the periodic table that we are in. So if we, in this example, are looking at zinc, well, the only thing for zinc that's going to react is the electrons that are in its outside energy levels. And so we don't care that it has 1s2 electrons or 2s2 or 2p, because those are buried inside. They're not going to react. The only things that are going to react are the electrons on the outside, the ones that can touch. For things to react, they need to touch, and it can't touch the things on the inside. So 3s2, 3p6, we don't care. All we really care about for zinc is these electrons that are in its outermost energy levels. So when we write that electron configuration, there's an abbreviated way to write it. What we do is we go back to the most recent noble gas, again, because it's noble, because it's stable, because that electron configuration, if it has an inner noble gas electron configuration, that part is not going to react. So in place of everything up to 3p6, we're going to put in symbol for argon, and then we'll write the electrons that are outside of it. So for this, the electron configuration for argon is 1s2, 2s2, 2p6, 3s2, p6. This, all we could abbreviate by writing argon, and then we'll write what electrons are outside. And so ultimately, after all of that, this is what we're getting to, is abbreviated electron configurations. So yes, you have to write orbital filling notations, you have to write full electron configurations, but ultimately this is what we're going to look at and use, is these noble gas abbreviated electron configurations. Notice here for our row 3, so these are row 3, or period 3 elements, things that have third energy levels. Notice they have their partial orbital filling diagrams listed. They have the full electron configuration. Notice sodium 1s2, 2s2, 2p6, 3s1. But again, all this stuff before really is not going to chemically react. All of that is neon. So you'd write neon and then just the outside energy, the outside electrons and the orbitals that they're in. And again, the ones that we are writing, remember what these are called. The outside S and P electrons are our valence electrons. And again, those are going to be the important ones when we look at chemical reactivity. So if there's a noble gas configuration within our element, we can substitute that out by the noble gas that it stands for, and then we can just write the electron configuration for the elements that we want. Or not elements, I'm sorry, but the electrons we want that are in the valence shell. The outermost S and P electrons are our valence electrons. So I'm going to do just one more here, and it's for chromium. And the reason I'm doing this one is because it's an exception to everything I just told you. Well, not everything, but some things. So if I write the full electron configuration, it's 1s2, 2s2. So this is it, 1s2, 2s2, 2p6, 3s2, 3p6, but then notice something funny happens here. What we have is we have 3d5 and then 4s1. Now remember what we said is that our 3d and our 4s electrons were actually really close in energy, and we actually fill our 4s before our 3d. But what happens in two elements that we have to worry about, in chromium, and then again we'll see the same type of behavior in copper, is that there's a level of stability when we have one electron in every available suborbital. So what happens is normally we would predict this to be 4s2, and then we'd be missing one electron right here. But we don't see that. What happens is that d orbital steals one electron from our s, so it can be half full or paramagnetic. And just like we said with nitrogen back, when you're half full in your outside energy level, there's some level of stability. So it is more stable for chromium to steal one electron from its 4s, to move it into its 3d, and we'll see a similar behavior with copper. What copper has is it is one way of having its d orbital filled. So if I write its 4s, it would be 4s2, and then in its 3d, it would be have 3d9. Notice it would be missing one. So copper actually steals that electron into its d, very similar to chromium. So if they're half full, or they're close to having the full outer shell, it might steal one electron. Again, this only happens between the s and the d electrons, so it doesn't happen for our p's. Our p's are too small, too different in energy, but our 4s, our 3d are really close. Similar thing with our 5s and our 4d that we'll see. Again, the only ones you need to be concerned about is chromium and copper. And notice those exceptions are listed really nicely here on this table, but here's kind of a nice synopsis, if you would, of what we've looked at. So we can write full electron configurations for our elements based on their number of electrons, again starting at the first energy level and then going up from there, which we can just read from the periodic table that we'd write in electron in a box diagram or our orbital filling diagram. That can be converted into our full electron configuration, or more appropriately, or not necessarily more appropriately, but maybe more usefully, we can write those as our noble gas configuration, where we only include the outermost electrons because those are the ones that are going to react.